It is my great pleasure to talk to you about two-dimensional NMR. I will also discuss briefly about Proton Nmr and give some examples. Please remember that science is fun and enjoyable. And we will see in this spectrum, I will start about electronegativity and the strongest factor affecting the chemical field, the chemical shift. In this regard, I would like to also do erratum about my previous first lecture regarding electron withdrawing group. This is inductive effect is the strongest effect. Why? Because electron withdrawing group, it means decrease electron density, accordingly deshielding of the nucleus. Consequently, the chemical shift will be increased. It means goes to the left-hand side. For example, if you have the methyl group, the normal chemical shift around 0.8. If you start to have carbonyl group, it means the oxygen started to withdraw the electrons from the methyl. This means decrease electron density of the methyl group. Then it is deshielded. It means increasing of the chemical shift. Furthermore, if the oxygen attached directly to the methyl, it means it is more electron withdrawing, more deshielded, more chemical shift. And finally, the floor, which is the strongest effect, and this is the maximum you can see the methyl group. It means that the electron withdrawing group affected the methyl group from the normal chemical shift at 0.8, imagine, until 4.2. This is a very big range, especially if the total range of proton NMR of the chemical shift of aliphatic and aromatic started from 0 until 8.4. This is half almost of it. It means that the electron withdrawing and the inductive effect is the strongest effect, right? And the vice versa, if it is electron donating group, of course, it will be increasing electron density and it will be make shielding. It means that the chemical shift will be toward this low chemical shift. Let us see some examples, and I will focus on alkaloids. Alkaloid, this is a proton NMR. Now, you will remember, here is the aliphatic region until 6.2. After that, aromatic region. And if the peak is like broad, it means functional group. So let us see what we will see. Here is the two protons. Now, I will give you new information. If the protons are not chemically and magnetically equivalent, it means they are different in the stereochemistry. It will give not only one value of the chemical shift, not only one delta, but two values. Why? Because they are two protons which are different in chemical shift. That's why you see the chemical shift of the first one and second one, axial and equatorial proton. And this is the advantage of NMR if you compare it with mass spectrometry. If the mass spectrometry, you cannot differentiate between the stereochemistry. But in proton NMR, this is the only way to differentiate, in addition, of course, of X-ray diffraction analysis, but X-ray is only for solid compound and it has to be crystalline. If you go further, the proton, next to proton, magnetically chemically equivalent, right? Next to proton, it is more deshielded. Why? Because it is alpha to the amino group. Finally, you will see that NH2 at this chemical shift. If you would like to approve NH2, now you recall it, then you can add DTO, and this chemical shift, the peak will be changed or will be disappeared. Now I will take you to another two-dimensional. What means two-dimensional? It means that you will have two spectra. Look, first spectra, second spectra, and both are chemical shift in the range of proton NMR. It means that you correlate proton with proton. We call it COSY, which means proton-proton correlation spectroscopy, because you correlate two spectra together. What is the aim of HH COSY? It is approval of two adjacent proton. So the adjacent proton, you remember, we can approve it by N+1 rule. But how can it help you? If, for example, you take these two proton, one proton at this chemical shift, it correlated, you can see, to proton at 4.1. It means the two protons are adjacent to each other. That's why you can make this square. So you see? Furthermore, for the stereochemistry, the other proton, it is here and it correlated with the same proton. Now you can understand why these two protons give different chemical shift. And now you can approve it by square of correlation. First is this proton correlated to this, and the other proton correlated to the second one. I think you agree with me now about how it is powerful technique and how you can enjoy with the spectra. I will take another spectra. Look to this. Here, Proton Nmr. Why? Chemical shift until 8. In this direction, it is until 99. Of course, it can be until 220, but since you don't need it, it is in the range of the aliphatic still, it means proton and the carbon. So it will be proton and the carbon correlation spectroscopy. It means it is one kind. The first kind of this correlation, it's called HSQC. What is the aim of HSQC? But if you know the chemical shift of the proton, like what we gained before, it is deshielded at 4.2. Look to this spot and correlate it to this, then you get the value of the carbon-13. So if you know the chemical shift of the proton, you can get the chemical shift of the carbon, or vice versa. So now you can see, DMSO, for example, it is at 2.5, then it correlated with the peak at almost 40. It means I could know the carbon-13 of the methyl group of DMSO. Another, this is a compound. Look to this CH2, which we approved before. You remember? It was 2, another approval. So these two proton, if you go down, then means the carbon-13 will be at 24. And why they are 2? Because one chemical shift, and this is the second chemical shift. Another methylene group, it is only 2 proton, but they are magnetically and chemical equivalent. It gives this carbon-13. The deshielded one at 54. Additionally, now you can see the factors affecting the chemical shift of the proton are the same factor affecting chemical shift of the carbon-13. How you can approve that? Because this proton at 4, which is deshielded, in the carbon-13 also it is deshielded and goes until 55. Another alkaloid compound. Now you can expect the chemical shift. We go together until here, then you will find that it is aliphatic until 5.7. Here, it is the aromatic region. And here, after 8.5, it means our functional group, right? So now you can do the assignment. Where is this methyl group attached to the double bond at 1.7? We go to CH2 at 1.7. Another CH2 attached to, it is directly attached to the oxygen. Then it is more chemical shift at 3.5, right? And the next one is even more deshielded. Why? Because it is ring size effect. It is inside the ring. Then it is more deshielded. So you see every small factor affecting in the proton Nmr. The next one, etc. Then this proton, it is even much more deshielded. It goes until 5.7. Why? Because it attached one side to oxygen and one side to nitrogen. So if it is attached to 2 atoms, then it is much more deshielded because of electron withdrawing group. And finally, the aromatic proton in the normal range. And now I could hear you that this is a functional group. Now, I will show you the spectra. Now we can see proton Nmr from chemical shift. And from chemical shift here, another proton. It means it is HH cozy. Could we see the correlation? We will give example, like these 2 proton. You recall where's the chemical shift? Then you can find the square here. So now it is approval of 2 adjacent proton. If you take another 2 proton, you will see, etc. Now I can hear you. What is this correlation? Proton, and this chemical shift is carbon. So why you see red color and the blue color? Because this we call it HSQC high sensitive, or it is HSQC with depth. It means the odd number like CH and the CH3 will be in red color. So all spot of red color is CH or CH3. So this is the first information. So the goal of HSQC depth, not only assignment of proton with carbon, but also it differentiates between CH3 and CH2. It means if you calculate here, you will find that the blue means CH2 and the red means CH or CH3. Additionally, of course, the CH3 will be maximum until here, but after that, it will be CH. Let us do the assignment of the compound. Now you can see this CH2 group. Now it is the aromatic, for example. It is in the aromatic region, right? Next one, which is deshielded, right? The CH, it is deshielded also in the carbon 13. That's why you see it at 885. The new one, etc., etc. So you can make the assignment of all the peaks this way. Now, if you take another example about this, now you can see it is many spots. Why many spots of the same proton? If you look here, one spot, 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 spot. In this range, it is proton. This range is carbon 13. So it is the same like before, but you have one factor extra, which is extra dots. In the previous one, it was only, I will be back again to you to show, every peak, it has only one spot. But this is different spots. Why? It means that it is long range coupling. So this proton with carbon, we call it HMBC. HMBC means that it's a correlation goes until carbon 3. So it is a correlation between proton, not only the proton carried by the same carbon, like HSQC, but the proton correlated to the carbon until bond 3. Let us take one example. If you take this OH group, so this is the H of the hydroxy group, right? We assign this already from Proton Nmr, then it will be correlated to the carbon. So not only to the carbon adjacent. Next one, it will be coupled to this proton of the carbon of the aromatic. Next one, it will be correlated again with this carbon. So you see? Now, I will give you another example of this aromatic, right? So the aromatic for coloration. So you can see that this proton correlated with this carbon, correlated with this carbon, correlated with this carbon here. So this is very big advantage that you can, by knowing the chemical shift of the proton, you can also assign the carbons until carbon number 3. I will take another example, which is a correlation. So you can practice by yourself of the rest of the peaks here. So because you have the assignment from the proton, then you can go down and you do the assignment of all the peaks in the same way like before. Now we go again to another example of Proton Nmr and of the chemical shift. You can see that here is the aliphatic region until 6.2, aromatic region, functional group. So look to the assignment, proton, and the other proton, more deshielded. Why? Because it is alpha to the amino group. Now you remember it, right? Aromatic, do you recall it? This is the alpha to hydroxy. Hydroxy group is electron donating group. So it means that it started to be here. What about if it is at meta position? Then it is not affected by electron donating group. Then it will be more deshielded. It will be at higher delta value like this. And this is what we call it before. You remember AB spectrum, when we say that you have a mirror image. A mirror image means that you will have AB spectrum, which is a phenomena. So if you see such a pattern in Proton Nmr, immediately you draw para-substitution. And now you recall that after 8.5, you will find the functional group of NH or hydroxy group or carboxylic group. We go to two-dimensional Nmr, proton and the proton spectra. And now you can see the correlation of the first two proton in the aliphatic region. And second correlation, next correlation on the aromatic. This is the AB spectrum. I think it is very clear that you have a square. So this two-dimensional is approval about each two adjacent carbon. If you couldn't see such such a square, it means that these two protons cannot be adjacent to each other. And this is the next example. Now I can hear you. What is this spectra? If you see the spots of red and the blue, and for each peak is only one, like this, it means, yes, HSQC. So this is the first proton. You could get the carbon-13. Second proton with more chemical shift of both. Third, next proton. And the aromatic region, it goes to 115. And the next one, which is para substitution. So now you can practice more and more, not only of the chemical shift, but also about the correlation of spectroscopy. I think you agree with me that NMR is easy. It just needs that you practice with many, many examples. And by the end of this lecture, I will leave you with some examples so you can stop the computer and you can practice by yourself in next. We go to another example of alkaloid. We try to assign before we go to the spectra. So what we can say in the aromatic region, this is alpha proton and this is meta, right? It means that you will see alpha, beta unsaturated, AB spectrum, sorry. And here is the aldehyde group. So you have the proton of the aldehyde group, which means a functional group, right? And in the aliphatic region, you remember alpha amino acid. What is the chemical shift? And protons here and protons here as well. In addition, of course, to the functional group. You can go to the spectra like that. Can you do the assignment? In a second, I will leave you to expect which is of which. Look to here. What you say about that? Immediately how you recognize. And this is aliphatic region and the functional group, right? Now you can go to the assignment. The CH2. CH is more deshielded. It is alpha to the carbonyl, right? Then the alpha amino group at almost 4, right? And then you can go to AB spectrum as we discussed before, and the aldehydic group is good practice. Now you can see to the carbon-13. What is about the chemical shift? This region, aliphatic until here, then it comes aromatic and double bond. And in the final, you will see the carbonyl group, which is specific, right? So you can do the assignment, proton of alpha, the more chemical shift of adjacent proton to the carbonyl group, and the one alpha amino group started aromatic, aromatic, aromatic again, aromatic, and carbonyl group, and finally carbonyl group with aldehydic group at the end of the spectra, right? You go to the two-dimensional NMR. What do we expect here? What you will expect here, right? Is these two protons will coupled together? Protons here will coupled together, proton here will coupled together. So if you can make a square of all these protons, it means it is correlated to each other. Now you can see these two protons, you find the square. Second, a square. Again, these two protons, alpha, beta saturated ketone, and finally, these two protons together, right? You go to this spectra as well, then you can see the assignment of the first proton, second, etc., the aromatic protons. But at the end, I can ask you a question. Why you don't see correlation of these last peaks here? There is no correlation at all. Do you know why? Because these are carbonyl groups, and these carbonyl groups, they don't have proton, right? Therefore, they will not see any correlation. This is carbonyl group, carbonyl group. It doesn't have proton. So you see only the correlation of proton with carbon. That's why we call it HSQC. Can we take another example? Yes, look with me. I will give you a second how you can do the assignment. Spectra, right? I think it is easy for you now. These two protons and the white is affected by the chemical shift. Next, alpha, AB spectrum, right? So this is the assignment of proton NMR. We go another example, right? So here is the first assignment, right? And why the next is more deshielded? Because now it affected by the nitrogen atom, and the next is more affected because it is double bond, right? If you go to the carbon 13, you will find the same. First is a methyl group. The second is methylene group, because of course is less proton. It means it is more deshielded. And then the carbon which affected by nitrogen, and the double bond in the area of the double bond, right? And finally, you will see the carbon 13, which is very spectacular because every peak in this area and more deshielded will be only carbon 13. If you go to the proton spectra, correlation first of the two adjacent proton and the correlation of next adjacent proton, but the others, you will not see any correlation because there is no proton here. Also this, no proton here. So you see only the correlation if two protons adjacent to each other. That's why we call it H cozy. But if you have proton here, but you don't have proton here, then you don't see these two correlations, right? If we get to next example, right? You started to take a second to do the assignment. And this, by the way, called the alpha beta unsaturated ketone. So this is new information for you. Why? Because this is carbonyl group, right? And here alpha and beta. This is only exception that you see aliphatic proton, but it is in the aromatic region. And why this happen? Because the effect of the carbonyl group with the double bond. So there are two effects, right? And this is how you do the assignment of the methyl group, methylene, and the other methylene, and the other methylene. Then we go to why you see it's in the aromatic region, because it is beta. Of course, if alpha here is occupied. So the only exception of the aromatic region again is this case of alpha beta unsaturated ketone, right? Then in the carbon 13 again, the methyl group first, then next is methylene groups. The methylene group attached to the nitrogen atom, which attached to oxygen atom, and again which attached here, and then the double bond, of course, it comes here, right? And then carbon 13 is very spectacular, as you could see, right? Go to cause spectrum, and before you see, now you can expect which protons you could see the adjacent, and you can make a square. You can practice here by yourself, right? If you see it like the solution, first square, second square. Now we go to another example, right? Can you do the assignment by yourself? Do you remember this proton? It will be in the aliphatic region or aromatic region. It is ketonic group and alpha beta. So alpha beta unsaturated ketone, it means this proton will be in the aromatic region, right? So the same, then you get the proton at 6.9, which is in the aromatic region. For the carbon 13, you can also practice with it. Aliphatic region first, then you go to the double bond region, and finally with the carbon 13. I hope you have enjoyed with my lecture, and please practice more, and I will show you more examples in the next lecture. Thank you very much, and thank you so much for my fantastic team. Without this team, I couldn't make any of these lectures available for you. Thank you.